Hello, so this is video number 2 of section 6.4. So like I promised in this video, we're going to basically use the Gram-Schmidt process, which we learned last time, to now calculate an orthonormal basis for a vector space, or for a subspace of, I guess I should say, R3. So if you'll recall, an orthonormal basis is just an orthogonal basis consisting of unit vectors and remember that we can actually given any vector, we can transform it into a unit vector in the same direction. And this means transform it into a unit vector that is a scalar multiple of the original vector by just dividing by its norm. And so we'll see how to do this in a second. But if we want to transform this into an orthogonal basis, first we're going to use the Gram-Schmidt process to find two orthogonal vectors, v1 and v2, that is just an orthogonal basis. For W. So we're going to start by doing exactly what we did last video. So remember, the Gram-Schmidt process tells us that v1, thankfully, is just equal to x1. So not much work to do for v1. And that v2 is equal to x2 minus the projection of x2 onto v1, which you might otherwise know as x2 dot v1 divided by v1 dot v1 times v1. And so this is equal to 4, -1, 2, minus x2 dot v1 is 8 plus 5 plus 2, so 15, divided by v1 dot v1, which is 2 squared, 4 plus 5 squared, 29 plus 1 squared is 30, divided by, not divided by, multiplied by the vector v1, 2, -5, 1. So this is equal to 1/2. So this is 4, -1, 2 minus 1/2 times 2, -5, 1. So 4 minus 1 is 3. -1 plus 5 halves is 3 halves. And 2 minus 1/2 is also equal to 3 halves. Let me double check. Yes. So our second vector, but again, remember, I don't like fractions, right? So I'm just going to multiply everything in this vector by 2 to get that our second vector given to us by the Gram-Schmidt process is the vector 6, 3, 3. So we can quickly check, are these orthogonal? Well, v1 dot v2 is equal to 6 times 2 plus -5 times 3 plus 1 times 3. This is 12 minus 15 plus 3, and so that adds up to 0. So just to double check, it's good to do that. There's a lot of, with dot products and arithmetic and all that, there's a lot going on, so it's always good to double check that when you think you have two vectors that are orthogonal, just quickly take the dot product and make sure they're orthogonal. And that tends to be a pretty safe way to check, right? If you get 0 there, then you can be pretty confident you've done everything correct up to this point. So the basis we just calculated, v1, v2, is an orthogonal basis. But if you'll recall, we want an orthonormal basis. So we now want two vectors, u1 and u2, that form an orthonormal basis. Well, so remember, we can always normalize any vector, that is, transform it into a unit vector, by dividing any vector by its norm. So we're going to let u1 equal the vector v1 divided by norm of v1, and we'll let u2 be the vector v2 divided by norm of v2. And so then each of these vectors will be unit vectors. u1 will be a scalar multiple of v1, u2 will be a scalar multiple of v2, so they'll still be orthogonal, and they'll span the same space as before. So here I will calculate the norms of each of these vectors. Remember, the norm of a vector is just the square root of the dot product of the vector with itself. So v1 dot v1, we've got square root of 30. And the norm of v2 is equal to v2 dot v2. So this is 6 squared plus 3 squared plus 3 squared, which is 36, plus 9 is 45, plus 9 is 54. And like I promised, we're going to get quite a few square roots involved in this. So remembering that u1 is norm of v1, or v1 divided by norm of v1, and u2 is v2 divided by norm of v2, we're just going to divide v1, or specifically each entry in v1, by the square root of 30. And each entry in u2 by the square root of 54. And so this is u1 and u2. This would be an orthonormal basis for the set spanned by x1 and x2. So a little bit of work at the end. We, in order to do this, have to use the Gram-Schmidt process to first find an orthogonal basis, calculate the norms of each of those vectors, then divide through by the norms in order to get unit vectors that are ultimately just scalar multiples of our original vectors. So, because oftentimes the Gram-Schmidt process is used in conjunction with what we just did. So oftentimes you'll, I'll make a note here. Oftentimes you actually will calculate an orthonormal basis using Gram-Schmidt. And so because of that, the Gram-Schmidt process is sometimes referred to as the Gram-Schmidt orthonormalization process. So sometimes you'll hear it referred to as this, and this is just to imply that after doing sort of the original Gram-Schmidt process as we know it, you can always do that last orthonormalization step in order to find an orthonormal basis. So, sort of changing directions a little bit for the rest of this section, this process also gives us a new form of, or a new type of factorization for any matrix A. So this is theorem 10 in your book, I think, 12. Theorem 12 in your book. And this is called a QR factorization of a matrix. So now that we have the ability to construct an orthonormal basis given any subset or any basis for a vector space, what we can do is factor A in this way. So if we have an m by n matrix with linearly independent columns, and this is important because this means that the columns of A themselves form a basis for the column space of A. So remember, if a matrix, so that would be a really good test question. If a matrix, right, the span of the columns of a matrix always span the column space, but don't always form a basis if those columns are not linearly dependent, right? But if the columns of A are linearly independent, then the columns themselves form a basis for the column space of A. So if A has linearly independent columns in this way, then A can be factored in the following form as A equals Q times R, where Q is a matrix with the same dimensions as A, an m by n matrix whose columns form an orthonormal basis for the column space of A. And so it's this line here, which specifically we now have the ability to find Q using the columns of A, which we'll see in a second. And R is a square n by n matrix that is upper triangular. With positive diagonal entries. So this type of a factorization specifically is very useful. If you remember the other, I think, LU factorization that we introduced had a lot of use in solving systems of equations. You might use this type of a factorization for that as well. But this also, I think, has applications in, in settings where we're actually looking at a matrix as a linear transformation, or wanting to study the eigenvalues of a matrix. This is useful. As we'll see, this is also useful in solving least squares problems, which we will do in later sections of this chapter. So I'm actually not going to go through a completely formal proof of this here. Basically, I'm just going to go through the steps of how to find a QR factorization, and then we will end the video, and actually the section as well, by calculating one for an actual matrix. So this is sort of the algorithm for finding a QR factorization. So remember I stated that since the columns of A are linearly independent, remember that means that if we can label the columns of A as A1 through AN, in this way, then this set of the columns of A exactly as they are is a basis for the column space of A, or just call A. So what does this mean? This means I have a basis for a subspace, so I can use the Gram-Schmidt, and now I actually will call it orthonormalization process. Orthonormalization process to construct an orthonormal basis for the column space of A. And this line here is exactly what we just did in the last example. You've got basically a set of vectors. You use Gram-Schmidt to find an orthogonal basis. Then you normalize each vector to find an orthonormal basis. And that's just going to be our matrix Q, is just the matrix whose columns we found in this way. So Q is relatively straightforward to find. And so notice, since Q is a matrix with orthonormal columns, we know something about Q. Specifically, we know that Q transpose times Q is equal to the n by n identity matrix. So this fact right here is going to help us find R. Because if Q times R is equal to A, then, well, Q transpose times Q times R is equal to Q transpose times A. And this implies that once I've found Q, I can find R by multiplying A by Q transpose on the left. So this simultaneously is more work and less work than it seems. The number of steps you have to do actually isn't that much. Well, the Gram-Schmidt process can sometimes be quite involved. But, you know, for as complicated as this originally seemed to me, finding Q and finding R seem remarkably simple, right? This seems like something that should be very hard to find, but, you know, Gram-Schmidt, as we saw, is lengthy, but not terribly, you know, I mean, it's relatively straightforward. And then, you know, it's kind of cool that because Q satisfies this property here, R sort of just, you can kind of just find R at the end by, you know, without having to do much work. And so I won't prove it here just for the sake of time, but the proof is in your book on page 359 that R satisfies the rest of the properties, that is being upper triangular and having positive entries on the diagonal. So I just want to wrap this up by actually calculating a QR factorization. Using this algorithm here. So we're going to let A be the following matrix. And you might recognize these column vectors because these are the same vectors we worked with in the last video. So then notice that by a previous example, these three vectors, v1, 1, 1, 1, 1, v2 equal to -3, 1, 1, 1, and, or sorry, V3 equal to 0, negative 2, 1, 1. Form an orthogonal basis for the column space of A. And so this is just because, again, if you separated these columns out, you'd notice that the three vectors defined by the columns of A are the three vectors we looked at in the second example of the previous video. Basically, I think myself and then the book sort of included chose this example so that we didn't have to go through the whole Gram-Schmidt process again, but pretend we found these vectors following the algorithm of the QR factorization algorithm by going through the Gram-Schmidt process. So, in order to find Q, remember, we don't want V1, V2, and V3. We want U1, U2, and U3, where each of these vectors are the normalized vectors we previously found. So here, the norm of V2, notice, is the square root of 3 squared plus 1 squared plus 1 squared plus 1 squared, which is 9 plus 1 plus 1 plus 1, which is 12. So this would be 1 over root 12 times negative 3, 1, 1, 1. The norm of V3 would be 4 plus, so 2 squared plus 1 squared plus 1 squared. This would be 1 over square root of 6 times 0, 2, 1, 1, negative 2, 1, 1. So dividing through by all of these, we'd get the Q in our QR factorization is the matrix 1 half, 1 half, 1 half, 1 half, V1 divided by its norm, negative 3 over root 12, 1 over root 12, 1 over root 12, 1 over root 12, which is V2 divided by its norm, and finally 0, negative 2 over root 6, 1 over root 6, and 1 over root 6, which is just V3 divided by its norm. So, almost done. Remember now, we know that R is equal to Q transpose times A. And so this is equal to the matrix 1 half, 1 half, 1 half, 1 half. So the matrix I'm writing out now is Q transpose. So Q transpose times A and as to not completely bore you with so much arithmetic, if you multiply these two matrices together, you should get the following matrix. Which is the R of our QR factorization for A. So these two matrices, Q and R, would give us a QR factorization for A. That is, A is equal to Q times R, where this is Q and this is R. So as you can see, by hand, this is maybe a little involved, but certainly this possesses some nice properties. Upper triangular matrices are always nice for finding eigenvalues, solving systems of equations. As you've already seen, in a lot of applications, upper triangular matrices, or sorry, not upper triangular matrices, matrices with orthonormal columns are very nice. They possess a lot of nice properties when looking at things as linear transformations. So, given that these two matrices possess so many nice properties, you can see why we might want to factor a matrix A into its QR factorization. So that wraps up section 6.4. Next we'll move into 6.5, which is least squares problems, and I guess I've said this a lot, this is also one of my most enjoyed sections because the application of what we're going to do is so cool.